Okay, bonjour. Yeah, don't get excited, that's where the French stops. Okay, so good morning. What I'm going to talk about today is, as would be suggested here, the art of Java type patterns. Actually, we're going to talk a little bit more than just Java type patterns. We're going to talk about Java patterns in general. My name's Simon Ritter. I'm the Deputy CTO at Azul. So first thing, let's talk a little bit about modern Java. What we've seen recently is a lot of changes to the core Java language. The switch to a 6-month release cadence for the JDK has enabled us to add more features more quickly than we were ever been able to do before. And I think this is a really good thing. We've seen lots of different things being added, and it means that developers are seeing the language progress and stay fresh and address the needs that they have. The way this is happening is, in terms of the language, through Project Amber. Now, Project Amber is a sort of bigger project, like Project Loom and Project Panama and various other ones. Valhalla is another example. But in terms of Project Amber, what it really is a collection of smaller things that they put together in terms of the changes to the language. If you look at the description, it says it's to explore and incubate smaller, productivity-oriented Java language features. And the other thing about having a 6-month release cadence is it means that we can now introduce things as preview features rather than immediately making them part of the standard. And that as well is a great idea because it means that there is time to solicit feedback, there's time for people to respond and say things that they like about a feature or things they don't like about a feature, and still have the opportunity to change it before it becomes part of the standard. And if you look at the way that this works is, again, the idea is that most features will go through at least 2 rounds of preview. So we're seeing that very much since JDK, well, sort of 10 really. And another nice thing that we see is that a lot of the features work separately, but they also work in conjunction with each other. And I have to say that people like Brian Gertz and Remy, who's sitting down here at the front, who are working on Project Amber, they really are doing an excellent job of figuring out how to move the language forward without breaking things and adding the features that people need. Okay, so let's talk a little bit about pattern matching in Java. So we have an API in Java that does pattern matching, java.util.regex. And we can do something like this, where we can say, let's create ourselves a pattern, which is something we want to match against. Then we can create a matcher, which will match on a particular string. And then if we really want to, we can call matches on that and return a Boolean. 3 lines of code, which we can also do in 1 line of code. We're not going to talk about this at all. This is not what we're here to talk about. This is a form of pattern matching, but it's not what we are going to address in this presentation. So let's talk a little bit about the fundamentals of pattern matching in terms of the language. This is not new. It's something that's been around really since the beginning of programming languages themselves. And back in the 1960s, the idea of pattern matching was introduced into various languages like Haskell, like awk. Quick show of hands, who's used awk? Okay, good, right, so we're in the right place. So let's talk about what we really mean by a pattern. A pattern consists of 2 things. So the first is we have a match predicate. This is a predicate, meaning that it's a thing that we can test against, and we can determine whether our pattern matches a particular target. Having got our predicate and being able to determine whether what we're testing against matches that target, we then have 1 or more pattern variables. And those pattern variables allow us to conditionally extract if the pattern matches. So as long as we match the pattern on the left-hand side, then we have the ability to use the pattern variables on the right-hand side. So this is, it's very simple, very straightforward in theory. There's a lot more to it though. And we have a number of different pattern types that we can think of. There's actually one more than this that I've listed here, but these are the ones I'm actually going to reference during the presentation. So the first of those is a constant pattern. And we've already seen this in Java because if you look at things like the switch statement, you are matching on a constant. So you do, case 1, case foo, whatever, and that's matching on a constant. And once you've matched on that, then you can go further in terms of what you do with your case statement. We then have the idea of a type pattern, which is what we're going to talk a lot about in this presentation, which is where we match on a specific type. Java, being an object-oriented language, has types, so we can match on those types. We also have the idea of a deconstruction pattern, which is where we can match on a particular type and we can extract things from it. Encapsulation is part of object orientation, so we can extract values from the encapsulated type. We also have the idea of a var pattern, which is where what we're doing is saying we don't actually care about the specific thing, so we want to match to anything and then be able to extract from that. And then the last one is what we call the any pattern, which is where we want to match on anything, but we don't actually want to use it, so we won't bind from the thing that we've matched to anything that we're going to use. And I'll kind of talk a little bit about that at the end. So before we get into pattern matching in terms of how we use it, we also need to talk a little bit about some of the things that have been added to Java since, well, JDK 9, and how they relate to what we're going to talk about in terms of the pattern matching. A couple of things we need to reference then. First is the introduction of switch expressions. So we've all seen in Java that we have the switch statement. It was included right from the very beginning. It was put there because the developers of Java wanted people who have programmed in C to feel comfortable and familiar with a lot of the syntax. They imported that directly, so the switch statement in Java works in exactly the same way as it does in C. That's both good and bad. It's good from the perspective that people understand how it works, but it's not so good from the fact that some of the way that it does work is a little bit less than ideal. I put here it's a rather clunky syntax. So the fact that you have to put a break statement in each of your case blocks, because if you don't, you fall through to the next one. It's designed to work that way. So let's have a quick show of hands. Who here has ever forgotten to put a break statement in? Yeah, there we go. That's one of the reasons why it's a great idea, but it has some drawbacks. Scoping of local variables can be a little bit counterintuitive, and also assignment of variables as well have some issues. So if we look at the way switch statement works, obviously we can take a very simple example, and this is a very common pattern of usage. We are switching on one variable, and we want to assign something to another variable. So in this case, we're going to assign to a number of letters based on the day of the week. Very straightforward, we're all familiar with this. And we can see how potentially we have a number of places where if we don't do things quite the right way, we're going to introduce bugs which could potentially be difficult to find. If we forget to put a break statement in, if we forget to assign a value to our number of letters, now, okay, if it's a local variable, that's easy enough, but if it's an instance variable, we could end up with a problem because we haven't assigned a value and the compiler won't catch that. So those are the sort of things we really don't want to be doing. And if you look at the way that we've now addressed that is through the idea of a switch expression. Introduced in JDK 12, nice idea, tidies up a number of the things which we saw on the previous slide. This is doing the same thing. What we're now doing is saying, let's assign a value to the number of letters, but we only have to do it once because the switch will return a value. It's now an expression. It evaluates and generates a result, rather than just being a statement that executes code. That's good because now we only have one place to remember to make that assignment. The second thing we can see is that we don't have break statements anymore, so we don't have to worry about forgetting to put a break statement in. We have values that are returned on the right-hand side of the arrow operator, borrowed that from the lambda expression. And the other thing that we can see here is that, and I find this hard to believe, that after 25 years, the developers of Java found this really cool feature. It's called a comma-separated list. And that means that now we don't have to put a case statement on each line. we can put all of the things on one line. 25 years to figure that out. But anyway, so that's all good. So the really key thing here is that we now have much more powerful code in terms of less code, but we haven't lost any of the readability. So this is really key to what we're doing. So switch expressions as well, one of the things we need to be aware of here is that they must be complete. They must be exhaustive in terms of values. And I'll come back and talk about this a little bit later when we do talk more about the pattern matching. The other thing we need to think about is algebraic data types in Java. And that includes two things. So the first thing is the idea of simple data class. In Java, we do this all the time. What we've got here is a class that represents a point. It has two values, a double x and a double y. In order to do that, we create a class, standard Java code. It has two instance variables, it has a constructor, it has two accessor methods. 14 lines of code to create a tuple. Wonderful. Now, I sort of said to Brian Gertz, I said, you know, why don't we have a tuple class in Java? And he said, yes, we could add tuple to the Java class, but then you're going to want a triple, then you want to quadruple. And, you know, where do we stop with these things? So the solution to this is records, introduced in JDK 14, a much simplified way of allowing data types to be included in the Java language. We can see here now that rather than having 14 lines of code for our record, we simply define it as a point with two values that we want to store in there, double x, double y, and because we're not doing anything in terms of the body of the record, it's all good, one line of code. Obviously we can, because a record is just a special form of class, if we want to use generics, that will work. And if we want to add more functionality to our record, then we can do that as well. Here we can include a static instance variable. We can't include any instance variables which are not declared in the record header, but we can include static instance variables if we want to, and we can include additional methods, you know, if we need that for whatever we're doing. A couple of other things to be aware of with records, and this is going to be important when we talk about things later on, is that the base class of all records is java.lang.record, meaning that a record cannot extend another class. It can implement interfaces, but it can't extend another class. If you want to, because it is just a class, you can override the equals, the hash code, and the toString methods. There are defaults provided, but you can use those if you want to. And the other thing about records is they are implicitly final, meaning you cannot extend them further. So this is, as Remy and I were talking about earlier, this is basically trying to get away from the idea of inheritance. The other thing about records is they don't follow the Java bean pattern, which means that rather than using getX as the accessor method, we just use the name of the variable x. This sometimes causes some issues if you're depending on the Java bean pattern to be implemented, but there is a way around this. Just call your variable getX or getY. It's not recommended, but it will work. The other thing we need to talk about is the idea of Java inheritance. Now, this is part of object orientation, and what we can see here is we've got a type hierarchy. We have a shape class, and then we have three subclasses of that, which are triangle, square, and pentagon. The thing that we don't have is any control, really, over who can subclass shape. The only thing that we can do in terms of subclassing shape or controlling it is to mark it as final. If we mark it as final, nobody can subclass it, but it's a all or nothing. And again, to introduce some more control on that in, let's see, JDK 15, was it? I think JDK 15 was the introduction of sealed classes. And what that allows us to do is to now change the way that we define shape. We have a new modifier which says that this class is sealed. So we say public sealed class shape, and then we add a permits clause which says that the list of classes after that are the permitted classes that can subclass shape. So obviously we've got triangle, square, and pentagon. Now if somebody was to come along and say, ooh, that shape class is really good, I like that, I want to subclass it, and I want to create a circle. won't work because circle is not listed in the permits clause, so we're not able to actually subclass it. The compiler will reject that and it will give you an error. All good. Now the other thing about sealed classes is that each subclass of a sealed class must specify its inheritance capabilities explicitly. And there are three different ways of doing that, so we'll see what those are. First is that we can continue to have a sealed class. In the case of our triangle, we can say that it is a sealed class triangle and it has another permits clause allowing equilateral and isosceles to extend from that. Second thing we could do as an alternative is we could prevent any further subclassing of that class. So we could say, in the case of our square, we make it final, nobody can then subclass it. And then the last thing that we can do is we can effectively unseal a class, and we can say, using another modifier, that this class pentagon is now non-sealed. And this is kind of interesting because this is the introduction of the first hyphenated keyword in Java language. And it's a contextual keyword. That's very important because having that as a contextual keyword means that it's only acting as a keyword in that particular position. Because of course you could declare a variable called an int non, an int sealed, and if you do non minus sealed, that's perfectly valid Java code. It's just that it won't work in the same way as a keyword at that particular point. So we have to have our inheritance capabilities expressed. Right, let's actually get on to the pattern matching side of things. So what do we have in terms of pattern matching currently in Java? Okay, well the first thing to look at is the use of the instanceof operator. Again, something that we've had right from the very beginning of the Java programming language. What we're doing here is we're saying that because Java is object-oriented, we can provide a reference to a type which we then want to have identified as a specific subtype. We can use polymorphism, so we can say, okay, we can specify that that is a supertype, but it could be a concrete class which is a subtype or a subtype of something else, and we need to determine which specific subtype it is. Yeah, we've done this ourselves many, many times. So the way that we use this is we say if obj is an instance of string. We're trying to determine if that reference that we have is a string. If it is, in order to use it as a string, we have to add this line of code here. So we have the explicit creation of a variable called s as a string, and then we have to assign to that obj with a cast. So explicitly cast from obj to string and do that. Then we can use it in our code. Now, that's kind of a bit of a pointless thing because if we're going to do that, we're always going to do the explicit cast in the assignment. So we're just sort of adding an extra line of code for no real value. So we must always perform that assignment with the explicit cast if we want to use that variable. In JDK 14, we had the introduction of pattern matching for instanceof. So this now allows us to do things in a slightly simpler, slightly more straightforward way. What we now do is we say if obj instanceof string, this is our pattern that we're going to match against, and then we introduce a binding variable s, which means that if we want to use obj as a string, we now have a reference s that can be treated as a string, and therefore we can call the methods on string and use that in exactly the way that we want to. Obviously in this case we have a conditional, we've got if statement. If it is a string, then within the true branch of that if statement, s will be a string and we can call the methods on it. In the false branch, we've failed the test, we haven't matched the pattern, so we haven't bound to the variable, which means that s is not valid in terms of its scope. We couldn't call a method on s because it isn't valid. Now we can take that further and we can actually technically use what's a guard here. And we can say if obj is an instance of string s and s.length is greater than 0. We can do this because we know that if we are evaluating an and, we always evaluate the left-hand side of the operator, and only if that equates to being true will we evaluate the right-hand side of the operator. If the left-hand side of the operator evaluates to true, then we know we have a string, which means that the scope of S will be valid on the right-hand side of the operator. So then when we do the test, it will work, and we can see if it is greater than 0. So all that code will work very nicely. If we tried to do that with an OR statement, that wouldn't work. The compiler would reject that. Because, again, we know that if we have an OR statement, we always evaluate the left-hand side, and only if that evaluates to false will we evaluate the right-hand side. If it evaluates to false, we don't have a string, therefore S would not be valid, wouldn't have scope, and we wouldn't be able to call the methods on it. So the compiler can reject that before you get to runtime. So that's good. We can eliminate that kind of error. Now, the way that the scoping works can be sometimes a little not counterintuitive, but you have to think about it a little bit more carefully, because we can invert that test, and we can say if not O instance of string, and have a binding variable to that. But we know that obviously this is now the false branch. If we have the false branch, we're going to return because we know we don't have a string. After that, the scope of S is still valid because we've bound to it, because we know that the test is true, so we do have a string, therefore we can use S in our code. So immediately after that, we can reference S and we can call s.length. We could have several hundred lines of code, and then we can still use S. The scope of S is valid right up until the end of that method. So this then introduces the idea of what we call flow scoping. And if you look at the way that local variables work, what you find is that the local variable, in terms of its scope, is valid from its declaration, and this is basically taken from the language spec, from its declaration until the end of the block in which it's declared. You know, we're familiar with this. If you declare a local variable in a method, you can use it in that method. If you declare a local variable in a for loop or a while loop, you can use it within that loop. If you declare it within a sub-block of code, then you can use it there. All good stuff. The other thing is that local variables are subject to definite assignment, meaning that we have to give a value to a local variable. Otherwise, the compiler will say the value may not have been set, and it won't allow you to compile it. Instance variables have default values. Local variables you have to assign. Again, we're familiar with all of this. This is nothing new. When we think about the binding variables in our pattern matching, what you'll find is that they are also subject to definite assignment. And that definite assignment is what actually determines their scope. Because what you'll find is that the scope of the binding variable is whichever place where the program, in the program, where it would have a definite assignment, so a definite value. And we can see that from the examples we've just seen. So wherever the pattern matches, and we can then reference that variable, that's where the scope is valid. And whether that's within the true branch of an if statement or after we've passed through the false branch and done a return. So it's where there would be definite assignment in that variable. So that's what we call flow scoping. But the scope is not the same as local variables. And there's a quite important thing here, because we can do something like this. We can say if O instance of integer, and then give it a binding variable which is num, and then we can have an else branch which says if O is an instance of float num, and again we can use num as the binding variable, same with a long. So the important thing is that the flow scoping for these means that the definite assignment is only where they're actually true, and we can reuse num in all three of these places. You wouldn't be able to do that with a local variable, but you can do it with a binding variable because it's only where it's actually valid. This is good because obviously we then don't have to have num1, num2, num3, or think up different names for our variables. Okay, so this is an interesting one. Right, question for you. Bit of code here. So I create an object S, and I assign it a new instance of an object. And then I do if S instance of string S. So my binding variable is the same name as my local variable. And if it is, I print out the length of the string. If it isn't, I print out no string. So who thinks this code will compile? Okay. Who thinks this code won't compile? I'm looking to Remy here because I want to see what he says. Okay, so the answer is yes and no. both. This is quantum superposition of Java code. Now, I found this very odd, and I still don't understand. If you put this into a file in your IDE and you try and compile this, it won't compile. Java-C will reject this quite validly because obviously we've already used s as a local variable, and it won't allow us to use it as a binding variable. So you think, okay, that's the answer. Except it's not, because if you use JShell, it will work. And I have no... It's a bug in JShell. Okay, good. I'm glad you said that. Because I have no idea why it would work in JShell, but it won't work in the compiler. Because I thought JShell was just built on top of Java-C, but I don't know. But I thought that was rather interesting. Next thing is pattern matching for switch. Now, we've seen in terms of the switch statement, switch expression. But what we can switch on are a very small set of types. So we can basically switch on integral values, we can switch on strings, and we can switch on enumerations. What we've now done is expand that so that we can have type patterns, and we can match on those. And we could do something like this. We can pass in an object reference to our method, and then we can switch on that reference, but now, rather than looking for a constant pattern that we would be doing before, we can now match on a type pattern. And I've got some examples here in the switch. So the first of these is very important. So we've introduced a new case which deals with null. So we didn't have that before, because if you think about the way that we had constants, the only place that really would have made any sense was in a string. But for enumerations and, well, maybe enumeration, but for enumerations and for integral values, we didn't use that. So we've introduced the idea of a specific case for null. And that way we can track that and we can test for it and say, okay, we've got a null. Then we can do our pattern matching on the type and have a binding variable. So we've got case string. We bind, if we have a string, to a variable called s. And then we can use that on the right-hand side of the arrow operator because the scope is valid. Similarly, if we've got a color, we can assign that to a binding variable called c, and we can call methods on that. Now, primitives in Java are not types. So we can't treat them as a type in the sense of a switch on a type pattern, but we can for arrays, because arrays of primitives are types. So we could have an int array bind to a variable ia, and then we can report the length on the right-hand side. And then we have a default, just to say we've got whatever other thing we have. Now null, and again I was talking to Remy about this earlier, so null's a little bit complicated in this situation. You would think that null is null, it's like, you know, it's just a null, so why is it complicated? Well, okay, we've introduced the case null here, and we can use case for null in switch statements and switch expressions. So we can use it wherever we want to now. If you do not include a case for null, then the compiler will insert one for you. And it will insert it at the top of the set of cases that you have. All it will do is simply say, if you've got a null, throw a null pointer exception. So the logic is nicely backwards compatible. It will do exactly what it did before. So you just simply throw a null pointer exception. But this has a slight sort of, you know, there's some subtlety to this. Because what we can do is we can do something like this. So we would say, okay, so let's not put a case for null in there. So we'll have the case for string, we'll have the case for color, int array, and a default. So in that case, what the compiler will do is add in the null for you, and that will throw a null pointer exception. So it works, all the code is great. Now, it might be the case that we actually want to do something with null specifically, and what we can then do is we can say, let's add null to default. So we can also say, we can say null or default, then we'll say bad input. So this is, well, like I say, it's a little bit sort of, you have to think about it in terms of what's going on. But you can add the null to the default, even though you might think, well, okay, it is a default, surely, but because the compiler inserts the null case for you, you have to explicitly call out the null on the default if you want to do that with the default, if that makes sense. Completeness. So this is where we have to, in the case of the switch statements and all switch expressions. So if we're doing a pattern switch statement and all switch expressions, they have to be exhaustive in terms of dealing with all possible values. So in this example here, I'm doing my type tester again, and I've got my switch on O, but this time I'm only dealing with string and integer. The question then is, what happens if I have a float, or if I have long, or something like that? Well, you could argue that, okay, it's not specified in the switch, so we simply go past there because we haven't matched against anything, and we just carry on. But that doesn't really kind of make sense. What we want to do is to say we need to deal with every possible type, so we would have to introduce a default. Right, so that's very clear, very easy. But we don't have to have a default in every single case. And this is where we can come back to what we were talking about earlier in terms of sealed types, or sealed classes, I should say. So sealed classes allow us to define a type hierarchy that is a closed set. And if we take the example we had before of the shape and the 3 subclasses, then we can have a tester which takes a shape as a parameter, and then we can switch on shape, and we can say, in the case of triangle, do this, in the case of square, do this, in the case of pentagon, do this. And because I made the shape superclass a concrete class, we have to also have a case for that, and then we can do something specifically for the shape. So this is covering all possible types that we have in that sealed type hierarchy. There is no other possibility, and so remembering that the compiler will insert the null for us. So we don't need to have a default in this particular case. Now we can also do guarded patterns, which is similar to what we had in terms of the use of the instanceof operator. Here what we're saying is, okay, we're going to switch on our shape again, but now what we're going to do is we're going to say, in the case of the triangle, then we're also going to add a conditional AND expression to that to say, if we have a triangle and we test the area of the triangle and say, if it's greater than 25, then we want to do this. Now, in order to be exhaustive, in order to be complete, we also have to have a case for just the triangle. Because, of course, if we failed the test on the right-hand side, we would still have a triangle, but we wouldn't have a case that would then be able to deal with that. So we must have a case underneath which says triangle without a guard. I mean, we could have more than one guard, but in this case, we're just saying, okay, if we fail that test, then we'll drop down and we'll see it's a triangle, we'll deal with it. Then we also deal with square, pentagon, and shape. So we can introduce this new idea of having a guard on that. Pattern dominance is also very important. So in this case, if I change the order, it will break my code. And I have to be careful about how I specify the order of the cases so that I have the right dominance for those things. Shape, being the superclass, will obviously match against any of those subclasses. If I make it my first case, then all things that I'm going to pass to it will match as a shape, because it's the superclass, so it'll work. But it means that I will never get to any of the subclasses below, and therefore it means the code is pretty pointless. The compiler will say, nope, can't do that, reject it, because you've got the supertype above the subtypes, and that would always match. So that won't compile. So shape always matches first, and then you get unreachable code for the rest of them. Similarly, if we use the guard, then we have to make sure that the order is correct for that as well. Because if we just had our triangle as the case first, that would match any triangle. We'd never get to the test on the area of the triangle as well. So it would be pointless having the second one. So you need to make sure that you get the order of the cases correct so that the dominance is right, so that you don't miss any of the ones subsequently. Pattern matching in future Java. What things might we expect to come that we haven't seen already? So pattern matching instance of and records. Okay, that's what we can do now. Now what we can do is we can then have the idea of a record. Wonderful. Okay, so we can have a record, and if we want to use that with instance of, we can do that. So we could say, okay, let's create a method called Pythagoras, takes an object. If O is an instance of point P. So we now have a binding variable for a point, and then we can extract from our record the values of X and Y. And then we can work out the hypotenuse of our triangle, in this case. This is good, but we can do better. So what we can do is we can say, okay, let's introduce the idea of pattern matching for records and use a record pattern, and in this case it's a deconstruction pattern. We're going to be able to extract things from that. So remember that since a record is just a special form of class, this will also work with standard classes as well. But it's called pattern matching for records, the way that it's defined at the moment. So what we can now do is we can say, let's have our Pythagoras method. We pass in object O. Now what we'll do is we say if O instance of, and we'll define the record in the binding variable. So we say point double X double Y. We know what the values are that we're going to have in that record. And then when we want to calculate the hypotenuse, we don't actually have to explicitly extract the values from that record, because now we have binding variables for the values inside the record. So our binding variables are X and Y, which the compiler will automatically extract from the record. We don't have to do that. So this is nice because it sort of tidies up some of the code. Now, patterns are also composable, which means that if we have a situation where we've got a point, so our record that we've already seen, let's introduce a enumeration called color, red, green, blue, and then we'll have another record which is a color point, which has a point and a color, very obviously. Then we can also have a color rectangle, which has two color points in it. And I've kind of like fiddled a bit here, because I've said let's implement shape on there. Now I know shape earlier was a concrete class, but in this case, because the record can't extend another class, we'll call shape an interface, and we'll say we implement it. So what we could then do is we could say print color, and we'll pass in a shape, because that's the interface that we've implemented in terms of our record. And we can say if S instance of color rectangle, and we can have these binding variables where we can say, right, we'll decompose it to say that we've got a color point top left and a color point bottom right, and then we can print out the top left color. Okay? But we know that top left is a record as well. So why don't we go further with that? So what we can do then is we can decompose that. And we can say color rectangle, and then decompose that and say that we've got a record color point, and introduce binding variables for point P and color C. That way we don't have to explicitly, again, dereference through the binding variable for the color point. We can simply reference the variable, the binding variable for the color. But point is a variable that is another record. So again, we could decompose that and compose it further. So we could say color rectangle, color point, point, double X, double Y. That introduces now our binding variables as X and Y, plus we've got color C and color point, in this case BR. And if we want to, we can just print out the value X. So we can compose these patterns, we can drill down, and that simplifies out, well, it may not look simplified here, but it does simplify things very nicely, because obviously in more complicated code, it's going to make things easier. Patterns and local variable type inference. So this is like things that aren't actually in the roadmap as far as I can see at the moment. But we've got the idea of local variable type inference in JDK 10. You can use var. And in this case, what we're doing is matching on any. So we could do something like this, where we could say color rectangle, color point, point, and then just say var x, var y, var c, var br, and let the compiler figure out for us what it is that we actually want to do. So the types involved there. But obviously, the compiler is going to need to figure out the exact types, and that we would need to have a situation where there aren't any different or sort of overloaded types of things. And then the last thing is the idea of the any pattern match. So this is not part of any JET that I've seen. And what we could do there is it's similar to the idea that was introduced in JET 302, which was lambda leftovers. And for those of you who are following the Java language very carefully, you'll know that in JDK 9, the underscore was disallowed as a variable name. Anybody here ever used underscore as a variable name? A couple of people. Yes, well, it doesn't matter because even though in JDK 9 an underscore is no longer a valid variable name, you can still use 2 or more underscores, so that will still work. But what the idea was there was to say, in a Lambda expression, if there was a parameter that you didn't care about, you could represent it as an underscore and just say, I don't care, I'm not going to use it on the left hand or the right hand side. So what we could do is, in a situation where we've got that more complicated piece of code, we can simply say, right, we know we've got a color point, we've got a point, and then we've got other things which make up that record. But the only thing we're interested in is the value of x. So let's highlight x as the binding variable that we actually want to use. Any of the other binding variables we simply represent as an underscore, and the compiler will say, well, okay, yes, I know you're not going to use it, so I will deal with it internally, but you don't have to worry about values and variable names for those. So I like that idea. It's quite nice to sort of tidy things up. And I have missed a semicolon on the end there, before anybody points that out to me. Finally, pattern matching for arrays is, again, taking this one step further. This was included in JET 405, is it? But it was included, but then they've withdrawn that from there. It's simply the idea of, again, decomposing and saying, if you've got an array, what you could do is, if O is an instance of an array of strings, and it's got a length greater than 2, well, okay, you could extract out the values from that and then print them out. What we could also do is we could use decomposition on that. We could say, if O is an instance of string, then create me the values as binding variables. So we've got string S1, string S2, then we'll use the varargs thing to say if there's any other values we don't care. And then we could do S1 plus S2. So we're using a binding variable to avoid the overhead of us having to include the boilerplate code to reference the individual array elements. So that's part of JET 405, but it was dropped for now. Just to summarize then, since I do 3 minutes, great. So pattern matching, I think, is a really powerful set of language constructs. It's going to simplify a number of common tasks. So we've seen that with the use of switch expressions and pattern matching in those types of situations, much less boilerplate code, more declarative. Also has the potential for better optimization underneath. If you look at some of the details of how this could be implemented, there is the possibility of getting better performance by using pattern matching rather than the way we do it at the moment. Some features are already there, some more are going to be included, and there might be more that will come in the future as well. So it's nice to see the way that the language is evolving. Just my one marketing slide, I'll just briefly mention that Azul, we do builds of OpenJDK, so you can get those from our website. They are free if you want to. That's the end of my marketing slide. So thank you very much. I've got 2 minutes for questions, but I will say afterwards, if you do want a t-shirt, I've got a bunch of t-shirts here at the front, so if people do want a t-shirt, please feel free to help yourself. I have less than 2 minutes for questions, so does anybody have a question? Okay. Oh. So I saw you, yep. So the question is, do you need a default with? Mm-hmm. So the question is, if you've got all the values represented, do you still need a default case? No, because as long as it is exhaustive, so long as it is complete, then you don't need a default. Because technically, it would never get to that default, because if you've covered everything already, then there's no default that it would actually match on. So you would never get to that point. So no, you wouldn't need a default. There's actually there's more complexity to it even than that, because if you look at things like enumerations, there's compile time versus runtime, and so there's this concept of remainder with these things. So, but I haven't got time to go into that now. But if you look at the specification for this, there's a lot more detail about how that will actually work. Yeah.
So you said you can unseal a class. So in this case, then you need to have the default again?
Yes, yes. So the question is, if you unseal a class, so in that example I gave you, Pentagon was unsealed. So technically, I suppose you would have to have a default in that example I gave you, because if it was unsealed, then you could potentially have a subclass of that, which, oh no, because the Pentagon would match, because it's the superclass. So yeah, you wouldn't need a default. I had to think about that one. Yeah, you wouldn't, because even though the Pentagon is unsealed, any subclass of that is still a Pentagon. So we have the case for Pentagon, therefore we don't need a default. Yeah. I've got 9 seconds. No, I'm over time. Hang on. One more question.
It's going up. But can you still specify a specific case for Pentagon?
Yes. Yeah. So you can specify a specific case for Pentagon. So the question was, can you specify specifically for Pentagon? Yes, you can. But you would then, if you wanted to, if you have subclasses of that, you could then have specific case statements for that, but you would have to put it above Pentagon to recognize it first. Okay, with that, I am definitely over time, so thank you very much.